So welcome back. We have we are discussing the modern block ciphers. We introduced their characteristics and the primitives behind them. Then we started discussing about the DES. So let us continue our interaction on the DES. These are the points which we need to look at in the DES. The number one, size of the plain text block. We said it is 64-bit. Size of the key is 64, and then it get formed to 56, right? Number of rounds we identified it is 16, right? Then we are going to talk about this round function. If you have noticed in the round function, what are the operations we have? We have substitution operation, we have permutation operation, we have combining the key, all those things. Then we need to discuss about the key scheduling process, right? So these are the things which we have to discuss. And so this is our the DES overview, right? So this is where we have actually stopped. So now let us continue our interaction. So on the plain text side, you have 64-bit length plain text. So the plain text passes through, what is the first step? What is the first step we said? It passes through first initial permutation. Now for that purpose you need a P box, and since we are doing it in the form of an initial permutation, it is also called as IP box, right? What is that IP box? This is the IP box, right? The IP box is a fixed, in the sense whenever you implement your DES, you have to take this box only. Now what it says? It says, what is this number indicates? 58. What does it mean? Now, in the original plain text, 64 bits, whatever is the 58th bit, that becomes first bit. What is the second bit in the after permutation? Whatever is the 50th bit, that becomes your second bit. So these are all indicating new bit positions, new bits derived from old or given text positions. Okay, this is called initial permutation. Next, so that means, imagine my plain text blocks are from M1 to M64, 64 bits. After permuting, what I get? How many bits I get? 64. So is it a straight, compressed, expanded? It's a straight P box. Okay. It's a straight P box. Just for your understanding, the first bit in the original given text, where it went, where is the first bit of M1 after permuting, where it went? It went somewhere here. Okay, this location is 40. Okay, when you do inverse permutation, how do your inverse permutation table looks? You need to do inverse permutation, right? When you will do the inverse permutation? After 16 rounds. When you do the inverse permutation, what would be the first bit? Your 40th bit would be the first bit, because your first bit went to the 40th location while doing initial permutation. So inverse permutation brings the 40th bit to the first location. Okay, that is how it gets done. Now this is a straightforward P box operation to perform initial permutation. Next, what is the second step? Once you do the initial permutation as per Feastel structures, what should be done? Divide into 2 halves. So, and then applying it through 16 rounds of operations. So, what happens in each round? In each round, what you actually first of all you are going to do is divide into 2 halves, left half of 32-bit and right half of 32-bit. And then what you do? Keep left half as it is, take the right half. This is your left and this is your right. This is your input given plain block? Input given plain block after transformation. After transformation is divided into 2 halves, which is left and then right. Keep the left half as it is of 32 bits, then take the right half, and then that right half, then what happens is that gets expanded to 48 bits. So this is your 32 and this is your 48. Okay. So for that purpose, what you do? What you take? On what you depend? P box. It's a permutation operation. Expansion. How do you expand? Using is it a straight P box? Expansion P box that you have, that you take, and you get 48 bit. That 48 bit gets bitwise XOR with key, round key. What is the round key size? 48 bit. Round key size is 48 bit. So when you XOR, it is a bitwise XOR operation, you get a 48 bit output that goes into a substitution operation. So input to the substitution operation is 48, output from the substitution operation is 32. A kind of compression you are doing. Okay. Then the output of this 32 undergoes permutation operation to produce a 32 bit. It's a straightforward, right? And then the output of that gets XORed with the left half. Okay. When you do that, the output is the new right and the old right is the new left. You understand? New left and the new right. Okay. This is what happens in each round. Like this, how many number of rounds? (16 rounds). Now then the point is, for every round what you need? For every round what you need? For every round you need a round key. How do you get? That is on the key schedule algorithm. What is actually your key size? 64-bit. And from that you got 56-bit. That 56-bit is divided into two halves, 28 and 28. 28 and 28. And in each half you do left shift. Left shift. That undergoes a permutation operation called PC choice PC2 table. So permutation operation. Output of that is 48-bit. That is going as the round key. Okay. So now you see there are so many steps involved. So what we do is this. How all these things happen? So we actually divide the whole thing into 5 steps on the text side. The other one is on the key side. That means the 6th step. Okay. Let us take these 6 steps. Are you able to follow? We will discuss this key expansion process also. Okay, don't worry. So now, what is the first step we need to understand? What is the first step? How do you do your 32-bit of right half getting expanded to 48-bit? So far what we did? So 64-bit of plain text. Is it that always you will have one 64-bit of plain text? Given plain text will have n number of blocks. We are discussing for one block. Then what you did, the next one? Initial permutation through IP table. Enter into the rounds. What you do in the round? Enter into the round. Take the right half. That's what we are here. So the right half of 32 gets expanded to how do you do that? For that purpose, you have to take a P box. That P box is not straightforward P box because you need to expand the 32 to 48. So what we the operation did was straightforward operation, write 1 to 32 bits. Write 1 to 32 bits. How many bits more are needed? 16 more. 8 bits on the left, 8 bits on the right. What are the bits? the bits are given here. Now how many bits have come? 48. So 32 plus 16, 48. And this E box or E table, which is nothing but a permutation operation, if you observe, now what is your first bit? 32nd bit. What is your second bit? First bit. So, like that. So your permutation operation is called as E through E table, okay, which is a fixed. That is the reason why we call this as a open design. Open design, right? Because what are the cryptographic primitives, the tables that are used in the DES algorithm is known to everybody. Tomorrow if you want to implement a DES algorithm, you have to follow this particular expansion table, right? So your 32 to 48 is done, right? Next. "48 bits of expanded text are," what is the next step? "Combined with the key." Which key? Right? That is the next step. That is the second step. So from key side, which is the round key of key, is combined via bitwise XOR to produce 48 bit, right? What is the next step? What is the next step? Apply substitution operation so that your 48 bit becomes 32 bit. So it is through S box. DES S box is the major core for the DES operation because this step brings nonlinearity in the DES and makes the DES more robust. What it do? The substitution operation is with the help of 8 S boxes. How many boxes? 8 S boxes. And each box is taking how many bits as input? 6 bit as input. So that means 8 into 6. So totally how many bits you are giving? 48. These 48 bits are given to 8 boxes. Each box is taking 6 bit as an input and each box is producing 4 bit as output. How many boxes? How many boxes? 8 boxes. How many bits they are producing each? 4, and hence 32 bits. So 48 gets into 32. This is the illustration. So you have 6 bits to each S box. So you have S box 1, S box 2, so on to 8 S boxes. Each box is taking bit 1, bit 2, bit 3 to bit 6, producing 4 bits, right? What are the 8 S boxes? These are the 8 S boxes. Okay, S box 1 to box 8. S box 1 to S box 8. How do you read them? We have already checked, right? So imagine, what is the size, input size to the each box? 6-bit input producing 4-bit output. So imagine this is your 6-bit input to first box. What is the first box? This is your first box. Okay. Now how do you do this? How do you handle this? So input is 0, 1, 1, 0, 0, 1. As per the logic we discussed a few minutes back, what is that you should do? You should take, no. How do you, the left and the leftmost actually there, but here you should take the left and the rightmost. Bits constitute your row. What is your row? 0, 0, 0, 1, 1, 0, 1, 1. Now, the left and rightmost bit indicates what? 0, 1. The middle bits indicate? Column. So 0, 0, 0, 2. The middle bits indicate column. So that means for 0, 1, 1, 0, 0, 1, what is that? This is your row and this is your column. What is the output? The output is 9. Is it 9 is the output? The binary equivalent of that is the output. What is the binary equivalent? It's 1001. Right? This is your output. So how many bits are given? 6 bits are given. Now producing 4 bits. Like this, how many boxes you have? 8 each box is producing 4 and totally you have 8 boxes, 8 into 4. Each box is taking 6, 8 into 6, and each box is producing 4, 8 into 4. Right. How these boxes are designed? How the boxes are designed? When I say, no, if you observe in the whole DES process, number of rounds, then your S box, P box, there are so many heuristics involved. All these are all chosen based on certain design criteria. There is a design criteria on which all these heuristics are designed. We don't deal with them, but now, once you have this, what is the next step? Your substitution operation output goes as input to permutation operation, right? So after this, permute the 32-bit. How do you permute? Using, you need to use some P box. what is that P box you have? Called permutation function box, which indicates, hey, look, bring this particular bit, put here. So what would be the first bit? The 16th bit is becoming the first bit. The 7th bit is becoming the second bit. The 20th bit is becoming the third bit, and so on. The P box is indicating the bit locations for the the operation. After that, what happens? Combined with using bitwise XOR. So once you do that, you get the output, which is the new write. What is the new left? The old write. With this, what we have completed is next. In the whole process, how many rounds we have? 16 rounds. Now for every round you need a subkey. How do you generate the subkey? So initially given key is the 64-bit length, and we need to make it 56-bit by ignoring every 8th bit. So every 8th bit is ignored. So that means the bit number 8, 16 and so on, and making this as the 56-bit key. Right? This is making it as 56-bit key. Once it is done, the next step is so truncate every 8th bit. Truncate every 8th bit. Then undergo the permutation operation, right, using a table called PC1 table. Okay. Again, the table is fixed. Nobody is expects somebody to remember all these tables. Okay. They're widely available. Okay. So generally student asks, is it table is asked in the exam, nobody asks. Okay. So these are all fixed tables. And then once you permute this 56-bit, they gets divided into two halves. Okay, 28-bit and 28-bit. Right? What is the next step? What is the next step? So divide the 56-bit permuted key into two halves, right? Then what is the next step? So we need to bring it to 48-bit round key. For that purpose, we have what was the step we discussed or we have mentioned earlier, that on both half you do circular shift. So on both halves perform circular shift. So they undergo a circular shift to the which side? Left. Left side circular shift. Okay. When I say shift to the left, how many bits? Either 1 or 2. Tell whether it is 1 or 2. 1, either 1 or 2. Now how many shifts you make, either one shift or two shift, is based on the round you are in. Okay. Imagine I am in the round 1, I make to the left. Imagine these are my bits. Say bit 1, bit 2, bit 3, bit 4, bit 5. What I do is left side 1 bit shift. Left side 1 bit shift, and it is circular if it is round 1. Imagine if it is round 2, also 1 bit. If it is round 3, I make it as 2 shifts. That means where B4 goes, where B3 goes, and where B2 goes, and B1 goes, because you are making to the left how many bit positions? 2. So what you did was perform circular shift, perform circular shift towards left by 1 or 2 bit positions. Based on the round we are in. Right? You are in first round, 1 bit position. Second round is also 1 bit position. But third round you are in to make 2 bit positions. Like that. That's fixed. See, this is to bring as much as random possible, because the subkeys should be same or should be different. Every subkey should be different to the maximum extent possible. Number 1. Number 2, every subkey is coming from, are they coming from heaven? No, they are coming from the key that is original key that is given. Okay. So these shifted values goes to another permutation operation. Why they should go? Because your job is to get that 48-bit key to the round. So what is that? This is my table which brings 48 bits from the shifted 56-bit positions. See, you have 2 halves, right? 28 and 28. That means that 56. And when they push it to that PC2, are you doing expansion or a straightforward or a compression? You have 56, 2 halves. Each half you have done the shifts operations. 56. Now you are making PC2, which is bringing 48 from it. Right? This brings that 48 which goes to the round as the round key. And not only that, whatever that you have shifted halves are there, they go as input to the next round. So in this round what happens? Again shifts happens, right? Left circular shift by how many bits? 1 or 2. Either 1 or 2 dependent on you are in the which round. So this left half and right half undergoes the shift operations for the next round. Again for the next round. Again for the next round. Okay? And from that you choose how many bits? 48 based on PC table. Okay. So PC table provides 48-bit to the round as round key, and what else? Whatever the shifted ones, they go as input to the next round subkey generation. Right? So this is how you produce the subkeys. So you see here the shifts off to the left. So left circular shifts either by 1 or 0 based on the round, produce this 56, and undergoes the PC table, produce this 48-bit, goes to every round. And then once you complete the round, the after 16 rounds, your 64-bit undergoes this 2 halves swap called 32-bit swap. That undergoes inverse initial permutation. Okay, because you did IP in the very beginning, that need to be inversed. This is your inverse table. What is the inverse table first bit? Inverse table first bit. Inverse table first bit is 40th. Why 40? Because while doing the initial permutation, where the first bit went? 40th location. Now you are bringing from the 40th location. So, okay. So this is the whole DES encryption algorithm. This is how the DES encryption algorithm works. And remember, it was introduced, okay. So it was introduced in late 70s, was in place in many commercial applications till early 90s. It was in place till early 90s, then got replaced with multiple DES, and subsequently early 2000s you have AES. Okay, so we saw the overall DES. When I say multiple DES, what does it mean? Multiple DES means it is double DES, triple DES. That means what you do? You take the plain text P, then encrypt with the help of DES. When I say E, so when I say E over P comma K1, what is this E? DES algorithm. Whole DES. That is the ciphertext. What do you mean by double DES? I take this C, which I don't call it as a C, I call it as a C1. I take this C1 and then I get the C to the final text by encrypting again that with again what? K2. Okay. Okay. Why people went for double DES? Now, what is the somebody asked, what is the plain text block size of DES? 64-bit block size, and it is fixed. You can't change. If you are dividing the blocks, you should divide into 64 bits only. Number one. Number two, again, what is the key size? 64-bit key, but actually it is 56-bit key, because you have removed 8 bits, it's a 56-bit key. With 56-bit key, what is the overall key space of DES? 2 to the power 2 to the power 56 is the overall key space of DES. So we said it was in place till 90s. The reason is, till that period, the systems were not able to crack the DES. Okay. Subsequently, cracking DES with the current generation systems, is a fraction of minutes. Performing, when I say crack, not a typical cryptanalytic attacks, rather a brute force attack. What is brute force? Explore all possible combination of the keys within a fraction of minutes, we can crack the DES. That is the reason. So my suggestion is, go back and then check. William Stallings is the best source if you want to understand, or Forozon, or the other day madam was mentioning about the Jonathan Cutts. So there are n varieties of books. If you are really interested to learn about the design criteria. What is the design criteria? If you notice, what are these boxes? How these S box, P box have come? How these various heuristics are fixed or has come into picture? These are the various things which you should read and understand. Okay. So what are the design features? All that. Why all this has happened? Okay. So how the decryption is happening? Okay. The beauty of this you should understand is one question. What is the question I asked in the very beginning? In the very beginning, I asked one question, and probably during the afternoon, you guys should explore and give the answer before end of the day to our the 2 TRAs. What is that? Number 1. Look at the this is the decryption. So this is all encryption, first round to 16th round. What is happening to the decryption? What is the input? Input is your ciphertext. So either you give the final round key to the receiver, or give the original key to the receiver and allow him to generate the keys. Okay. So you start from the ciphertext and the 16th round key and go reverse to perform decryption. Right. So we go back to get back your plain text. Now everything appears fair and straightforward, except some things. What are that? No, sorry? Permutations. Okay. If you notice the initial permutation and final permutation, you give 64 bit, you got 64 bit, right? What are that is not so straightforward that it appears? Decryption is supposed to be the reverse process of encryption. What is the question I asked in the very beginning? There are certain boxes which we have used, which are number one, compression boxes and expansion boxes, right? Where we have used, you remember your 32 bit of 32 bit of right half is expanded to 48 bit through which operation? P operation. 48 bit of the combined XR key is has underwent which operation? Which operation? Producing through. Are these boxes invertible? Then how we are able to produce the decryption? We are using in the structure certain non-invertible components. We are aiming for a decryption process which is supposed to be reversible. What is happening? That is the question I asked, right? So, XR where? So look at this. No, look at this XR operation. So bitwise XR, there is no problem. What is that we are talking about? No. You mentioned about the XR. I am talking about the non-invertible components in the structure. I am talking about them. The bitwise XR operation, see, first of all, we go for the logical operation of XR for the purpose of making it reverse, right? That is fair enough. No worries. Similarly, you have certain straight P boxes, no worries at all. No, you think on that, and there is some words you have used. There itself lies the answer. Think on that. So, there are so many examples which you can try online. I don't go with this ones. So if you notice, there is a plain text given. So once you do the initial permutation, what happens? Then picking the left half and right half, then round 1, round 2, so on, the round keys. Okay. See, remember, it appears, after our discussion that, DES is a very complex process or not. But remember, the other day also it was concluded, discussed that between symmetric and asymmetric ciphers, which are less computationally expensive, symmetrics, right? So play with these calculators which are there online. You can our people will share it with you. You can perform this encryption and decryption operations you can do online. Okay, so just play with these online DES calculators, right? So now the point is this: we said with 56-bit key, with the current systems or the systems that are performing 10 power 13 calculations, decryptions per second, they can break. I repeat, the systems that perform 10 power 13 decryptions per second can break the DES through brute force attack in a matter of 1 hour. Okay. Now, you may get a doubt. See, in a practical scenario, sometimes when you forget the password, what happens in the system? You forget the password, you try hitting multiple passwords. What will happen? Will it allow you to perform brute force attack? After 5-6 attempts, what happens? It lock your account. Then why we are thinking that, whether brute force attack is possible in 1 hour? My account gets, if suppose somebody makes a brute force attack, system blocks. Okay, no problem, then I go for DES. I can go for DES, right? See, the point is, yes, the system blocks after 2-3 attempts or 4-5 attempts. Will that I consider as DES is secure? DES is not secure. Since DES is not secure, what I did? I put that extra layer of blocking the account within 2-3 attempts. So, generally we think that brute force attack, why do we take it? When a practical scenario, brute force attacks are nullified through the systems by making the system, account lock or your access locked, access denied, all that happens, right? Is it part of the DES or any cryptographic algorithm? No, it is on top of that, there is an extra layer of security, right? Preventing the access upon couple of unsuccessful attempts, right? So, nevertheless, so people realized that, yes, going for DES in all, is a very, this one. Okay. I skipped this avalanche effect and the other effects. Okay, and the design principles and the design for this one. So, what people did was, they went for multiple DES. So, why? By going for multiple double DES, what I can get? By going for double DES, what I can get? Increase the key space, right? I can increase my key space. So, what happened? You take the plain text, encrypt with the help of which algorithm is this? E? With the help of K1, take the ciphertext. Of course, it is represented as X, which is the intermediate ciphertext. Again, encrypt it with the help of DES and apply a different key K2. Right, and produce the ciphertext. Then what happens? At the sender, this is what happens, and at the receiver, take the ciphertext, then decrypt it with the help of which key? K2, because which lock you have used? The second lock is the last. So, open that second lock. That means K2 has to be used to decrypt it. What you get is the intermediate ciphertext, right? Then take the first key, decrypt it to get the plain text block back. So, you can increase the key space, right? So, that is double DES. Sometimes what happen, in the name of increasing the or in the name of improving the structure, this brings a kind of vulnerability, which is unknown or unintentionally brought vulnerability. What is that vulnerability? It is called meet in the middle attack. It is called meet in the middle attack, which is actually not there in the DES, right? What is meet in middle attack is this. Okay, given a pair which is the plain text and the ciphertext, the attack goes this way. Okay, first, what the attacker would do, attacker take the plain text and perform a brute force attack with the help of 2 power 56 all possible combinations of key, which is K1. Okay, that means he is doing the plain text encryption with the help of all possible, that means it's a brute force attack. Okay, what is the operation is doing? What is the operation is doing? Encrypting. Number one, can he do encryption or not? He can do encryption. Anybody can do encryption. Number one. When this is possible? If the attacker knows some information. What is the information? Known plain text attack. What is that? P comma C, a pair. Some plain text and its corresponding ciphertext. What that gentleman did? Took the plain text of P, encrypted that with all possible combinations of keys. Within how many minutes he can do? As we saw, maybe with that system that is calculating 10 power 13 calculations at this one, it can do within 1 hour. Parallelly, what he did also is, he also took C. What he did? He also took C, because he has C, right? The corresponding C. He performed the decryption operation with all possible combinations of K2. Again, how much time he can do? Actually, both he can do in 1 hour, right? If you have a system, a multi environment system, he can do simultaneously and finish the matter. What he did is, first he tried the encryption of plain text with all possible combinations of first key and put that result in a database, took the ciphertext, decrypted with all possible combinations of the second key, put it in the database. Then what he will do next? He just find out the match where your intermediate texts, when you encrypt the first piece with the first set of key and that intermediate text, when you decrypt that ciphertext with the second key and the intermediate text, when these intermediate texts are matching, what does that indicate? The two keys, K1, K2. Are you able to follow? So, this is a severe vulnerability that came because of what? Double encryption. Is it because of the double encryption it came? No, it is the way in which the double encryption is done. Okay, so there is an example in one of the book wherein which you can see that he took the plain text. The plain text ciphertext combination is 3 and 189. So what he did, took the plain text 3, explored with all possible combinations of the key, and this is the intermediate ciphertext. And then this is the ciphertext explored with all possible combinations of K2, and this is the intermediate ciphertext. Right? So then what you do? You find where the matches are coming and pick those keys. Then your keys comes K1, K2. Right? So this is called meet in the middle attack, and because of that, people not gone for double DES, people went for triple DES. People went for triple DES. What is the triple DES is doing? What the triple DES do is, you take the plain text, encrypt with the help of the first key, and perform then the decryption operation with the help of second key. Decryption operation with the help of first key produces what? But decryption operation is performed with the help of second key. What it produce? Ciphertext. Ciphertext. So multiple DES, especially the triple DES, the sequence of operation is encrypt, decrypt, encrypt. When I say encrypt, decrypt, encrypt, it is not that actually you are doing decryption, you are actually doing the encryption process only. And the receiver decryption, if you notice, you see that decryption, encryption, decryption. Though you have encryption in the decryption process, you are actually doing the decryption. The reason is you are supplying the different key. Okay. And a point is that you see here, this is triple DES with 2 keys. That means encrypt with the first key over the plain text, get the intermediate ciphertext, and perform the decryption using the second key, get the ciphertext, and encrypt with the help of again the first key. So 2 keys. No sir, I will use 3 keys. No worries, you can use always 3 keys. Okay. How do you do that then? So even if you use 3 keys, then what happens? K1, K2, K3. Right? So encrypt with K1, decrypt with K2, encrypt with K3. The point is that, what will become your overhead? Number 1, you need to generate the keys. Anyway, it's a random bit strings. Number 2 is, you actually have always the overhead of key exchange, because this is what cipher? It is symmetric ciphers. Symmetric ciphers challenge is, okay. So you can go with this also. Even now, in some of the very few applications, triple DES is in place. In some of the few applications, such as, especially mail applications such as PGP, which stands for Pretty Good Privacy, Secure Multi-Purpose Internet Mail Exchange, SMIME. In these applications, you have still triple DES is in place. Now, once you understand this triple DES, there are n varieties of the algorithms which are symmetric in nature, and this one, symmetric block ciphers. Okay. Any doubts on this? Any doubts on this? So if next we go for AES, which is Advanced Encryption Standard. So before that, any doubts? So if no more doubts, if no doubts, what I want you is, you can do this. Go to, already the team has given you certain set of programs. Please do those programs. In addition to that, please go to this lab, cryptography lab in IIT Hyderabad. Okay, so you can Google it, and then this one. So you can go to this lab, and it's a virtual lab, wherein which you can go to this list of experiments. There are about 10 experiments given in this virtual lab, and here you can see each experiment. For each experiment, they gave a narration which includes, the process, that means the algorithms that are there, and what is the experiment about. Then, the procedure for the procedure of breaking the shift cipher. You know the shift cipher, right? We have already discussed, right? Now they gave examples. Then on top of that, they gave a simulation. The simulation, actually, you can play with these, by giving different ciphertext. You can see that, you can have your own shifts, shift by 5, shift by 0, shift by 10, shift by whatever it is, so out of 26, you have these ones. So shift, so try this. Then this is only a simulation. Then what you do is go to the assignment, So you need to solve these problems. There are certain problems given. Of course, you can use this platform itself. You need not again code. That coding already our team has given. So you need to solve this. This one. So you can go to this and break the shift cipher. Then you have monoalphabetic substitution ciphers. Then one-time pad. Then you have DES, right? So this also you can go to the symmetric key DES. This also you can this one. Of course, we have other AES and all that. So that you can practice. If you are already familiar with AES, you can practice. Otherwise, we will have discussion and then we can proceed. Okay. So one of the feature the DES has, or not only for the DES, any of these cryptographic algorithms, we saw various, the various the heuristics involved. On what basis? One of the basic functionality, basic feature is the avalanche effect. Okay. So the avalanche effect, if you notice, what is the avalanche effect is that, any small change in either the plain text or the key should produce a major significant change in the ciphertext. This is the called avalanche effect. Okay. So that means even with a single bit position change, how much bit difference that it produces in the ciphertext. Okay. So take an example. Imagine you are given with two texts. One is all zeros, and what is the other text is just one bit difference on the leftmost, and the rest of the text is same. Okay. And you notice the key. Okay, this is the key. So if you see the operation of DES on these two plain texts with the same key, how many rounds you have? 16 rounds, right? So 16 rounds. When you start at the round 0, what is the difference between these two plain texts? How many bits? Only one, right? How many bits are differ in the when this one is given? Only one. But by the time you complete the first round, both plain text, once they complete the first round, they differ in 6 bits. By the time they complete, say, third round, they differ by 35 bits. By the time they complete the fourth round, 39 bits. So even you notice that at the end of 10th round, they differ by 44 bits, which is a major enormous, almost more than half of the bits. But actually speaking, how many bits the plain text is differ by? Only one. A single small change in the plain text is producing a major change in the resultant ciphertext. This is called your avalanche effect. Of course, we go for 16 rounds, so at the end of 16th round, you have 34 bits differs. right? So this is called avalanche effect. Okay, not only for DES, any encryption algorithm. The other day somebody said, sir, I want to come out with my own algorithm. Obviously you can come out, but whenever you want to come out with your own algorithm, it should meet certain design criteria of encryption algorithms. Okay, and above that, if you actually want to have it, make it commercial, there is agency, like there are certain standard agencies such as NIST. NIST, which is the standard international agency that says that yes, this algorithm is of commercial standard. Then not only NIST, we have ITRU. Okay, then we have IEEE. Okay, like this, there are various the agencies that brings standards. Okay, that brings the standards. And not only that, so once you have understood these aspects, in the very beginning we said my crypto system, when I'm saying that I am coming out with the crypto solution, in the very beginning I said when I'm coming out with a crypto solution for a given security problem, what I should have? A symmetric key algorithm providing the confidentiality, a asymmetric key algorithm providing key exchange, a kind of keyless ciphers such as hash functions or MAC functions to provide authentication and integrity. Then only you say that I've come out with a full-fledged security solution. Okay, is that fair? Okay, so we'll stop here and we'll break for lunch and then come back, or you want to start playing those ciphers and then go for lunch, is your choice. Okay.